Welcome to science class. Today we are going to begin learning about the processes of weathering and erosion. I have talked about this a lot before, especially in the sedimentary rocks video, but specifically in this unit I will be showing you how rivers, glaciers, and the wind changes Earth's landscapes. Earth's natural beauty really comes from erosion. Look at these structures that make up the gorgeous landscape of Bryce Canyon in Utah. Notice how they're all incredibly uniform. That's the telltale sign of the type of erosion that produces them, which is water erosion in this case. These columnar rock formations are known as hoodoos. Mountains are carved primarily by ice, either from glaciers or seasonal ice. Then of course there are rivers, which cut through mountains, plains, canyons, and plateaus. But the details of all that and more will be covered in the next two videos. Today, I just want to cover what weathering is and what the primary means by which it is carried out are. Let's get started. Weathering is simply defined as the process of breaking down the solid earth on the surface, rocks turning into sediment. That's what weathering is. Erosion, meanwhile, is the transport of sediments. The wind, flowing water, ice, these things both weather and erode the surface. Living things and certain geological processes contribute to weathering, but not erosion. The reason weathering is possible on Earth is because of, wait for it, the weather. The energy for these processes is derived from the sun, which causes the water cycle and other atmospheric processes that make our planet dynamic. So then, here's a question. Does weathering happen on other planets? Yes, but not like on Earth. Actually, some moons have dynamic surfaces. As badly as I want to get into this, we're going to have to wait for our astronomy unit for that, but I'll cover Pluto briefly. Pluto has mountains and plains and even glaciers. Looking at the moon or Mercury, we can see that both are totally covered in craters. The surfaces of these planets do not change because they have no atmosphere, water, ices, or tectonic activity. Meanwhile, Pluto is far less cratered, meaning its surface is reformed slowly but constantly. The mountains on Pluto can be upwards of 3,500 meters tall, which is very impressive, but these mountains are made of ices, frozen solid water, methane, and nitrogen. Glaciers that flow slowly carve through parts of Pluto's terrain, which is one way weathering and erosion happens. Another much more exotic way, which doesn't occur on Earth, is evaporation. Because the surface of Pluto is made of ices and not rocks, it can be broken down and sculpted by evaporation. Rocks on Earth obviously don't evaporate, so that's why the answer to the question of does weathering happen on other planets was yes, but not like on Earth. Oh, and I'm not calling Pluto a planet because it's not. It's a dwarf planet. Get over it. Again, we'll have to wait until the astronomy unit to talk about why. Here on Earth, there are two kinds of weathering, mechanical and chemical. Mechanical weathering occurs when physical forces break rock down into smaller and smaller pieces. It is important to note that the mineral composition of the rock does not change. Chemical weathering is carried out by the dissolving power of water, and it does indeed change the composition of the rock. But we're going to keep going with mechanical weathering first. 4 forces cause mechanical weathering: frost wedging, unloading, and biological activity, and gravity. When water freezes, its volume increases by 9%, and with tremendous force. In fact, ice can push with a maximum force of something like 30,000 psi, pounds per square inch, which is over 2,100 kilograms per centimeter squared. That's the weight of a Ford F-150 pushing on an area this big. So yeah, ice can break rocks apart. That's what frost wedging is. This is primarily what wears down mountains that don't have permanent glaciers. Temperate regions or high elevation areas see a lot of frost wedging. We call the broken rock fragments produced by frost wedging talus. Strictly speaking, this is not what glaciers do. Glaciers are in constant motion, so glaciers really are eroding sediment, not weathering it. Understand also that these processes occur very slowly. Look at Devil's Tower. It's littered on all sides with a boulder field of its own columns of rock that have been broken off from a combination of gravity and frost wedging. There are thousands of these boulders, but nobody has ever seen a single one drop from the formation. The Grand Canyon is hundreds of kilometers long and can be more than 30 kilometers wide, and is visited by 5 million people a year. But rock slides are virtually never seen or heard. You'd think the force that produced a structure that enormous would be witnessed constantly, but no. Earth is incredibly ancient, and its surface, while dynamic, virtually never changes right in front of our eyes. Unloading, the next mechanical weathering process, is a process that specifically influences igneous rocks. Intrusive igneous rocks, you will recall, form deep within the earth under extreme pressure. Tectonic uplift and erosion, however, can expose this once buried rock formation to the surface. Then something weird can happen. The rock can actually begin to expand upwards as the pressure is reduced. I know that sounds odd, but the original igneous rock body, which is known as a pluton, can be absolutely gigantic. All of the granite in Yosemite National Park is technically one unit. It's been broken down and disconnected on the surface today, but all of the granite is uniform and formed at the same time. So let's say the formation is 1,000 meters tall and it expands by just 0.1%, which seems reasonable. That still means an expansion of 1 meter, which is significant. Rocks obviously aren't flexible, so this expansion causes portions in the outer surfaces of the rocks to break off. That's actually the real weathering here, and that process is called exfoliation. If we zoom in here on Half Dome, probably the most iconic structure in Yosemite, you can see where portions of its exterior have flaked off, and even what looks like stretch marks all over its surface, as it was birthed from inside the planet. Living things contribute to both chemical and mechanical weathering. Plant roots are really the only meaningful activity living things do that physically reduces rocks. Us humans dynamite portions of mountains away to build roads and extract resources, and although we are doing this on massive scales, it's really not the case that this reduces the surface like plants, which are literally everywhere, do. Gravity weathers rock simply by tearing down exposed rock surfaces. Gravity can only do this once the rock has been sufficiently weakened by other types of weathering, from the water or wind or otherwise. So that was mechanical weathering. Now on to chemical weathering. Weathering a rock chemically means that you alter its composition. Chemical weathering is impossible without water, and it is carried out exclusively by water. Well, okay, living things chemically weather rock also. Some organisms release weak acids that dissolve rock away, but this really doesn't amount to anything. Say there was a planet identical to Earth in every way except it had no life. Weathering and erosion would not be in any meaningful way different between these two worlds. So I'm only going to talk about water now. Rainwater is just barely acidic, but this is enough over time to dissolve away huge volumes of rock. Water gets its acidity from carbon dioxide and sulfur compounds that mix with clouds in the atmosphere. As the rock is weakened by chemical weathering, large sections can then crumble away as gravity pulls on them. Yellowstone Canyon is a beautiful landscape, but it didn't always exist. This is hard to picture, but the waterfall in the distance used to be much closer. As the water rushes over the edge, it slowly dissolves away and grinds away at the edge of the overhang, and over millennia, it retreats. One day, the waterfall will retreat all the way back through sections of the river which today are flat plains, but they too will become part of the canyon. Not all of a rock is dissolved and turned into a solution from chemical weathering. Only the weak minerals do this, which is why we say chemical weathering changes the composition of rock. Beach sand is mostly silica, but those sand grains didn't form separate from each other. The sediment of a beach was once part of a single rock structure. Weak minerals like feldspar dissolve away into solution, while the silica quartz crystals are freed and accumulate. Because of the nature of how water works on a surface, it tends to smooth out solid rock formations. This is called spheroidal weathering. Soft sedimentary rock layers like in Bryce Canyon or the Grand Canyon don't do this because the rock is not solid enough, so it just crumbles as it is worn away. Weathering is influenced by environmental factors, chief among which is climate. An area that is seasonal will typically have a greater rate of weathering and erosion. Seasonal changes allow ice to melt and reform, even from day to day, so the processes of frost wedging are at work. The seasonality also means that water will cycle rather than just stay frozen. As mechanical forces break rock apart, the rate of chemical weathering is actually increased. Weathering can only occur on the surface, so as more surfaces are exposed, the quicker a rock can dissolve in water. Dry desert-like climates, seasonal climates, and polar climates tend to produce mostly mechanical weathering because you have the work of the ice or wind-blown sand working on the rock. More tropical, or at least wet climates, not all of which are tropical, have greater amounts of chemical weathering. This isn't exactly the case all of the time, but it's a pretty good rule of thumb. The characteristics of rock are also influential in the rate at which weathering occurs. Certain rocks and minerals just erode more slowly than others. The Badlands and Bryce Canyon are composed of very soft sedimentary rock, and sadly, both of these landscapes will be reduced to dust and flat area really not very long from now in geologic terms. That still means a couple million years, but that's really nothing in the grand scheme of things. Meanwhile, the granite peaks of the Black Hills will weather the storm for much longer, even though they're right next to the Badlands. You can see the effects of rock characteristics in graveyards. Take a look at George Hare's epitaph or tombstone. George died in March, although I'm not sure what day. I'm pretty sure the year was 1887, but it could also be 1862. And I think George was aged 20 years, but maybe it says 29. The rest of George's story on the bottom is totally lost, but we can see something was written there. Now look at Nathaniel Currier's tombstone. He died extremely close to the same time as George, and although there's not much written here, it's very easy to read. George's tombstone is made of marble, which, although it is a metamorphic rock, is much less tolerant to chemical weathering than granite, which is what Nathaniel's tombstone is made of. This gargoyle also has seen much better days. Honestly, don't know what this is made of, but it looks like marble. Chemical weathering has reduced all of the finer details of the eyes, face, hair, and whatever else might have been sculpted there. Next time, we are going to focus solely on the works of rivers, which weather and erode the greatest volume of Earth's surface by far. Thanks for watching.